time orientation. So if you have a vector, a time-like vector, okay, we talked about what it means for a vector to be time-like. What does it mean for a vector to be time-like?
Slow to speed of light.
Yeah, slower to the speed of light. But from a very calculational sense, what does it mean for a vector to be time-like? So I'm going to, if this is, what did I use, x0 or x1?
If a squared is less than 0.
Yeah,
Yeah,
x squared is less than 0.
So suppose I call this x1, this point x1, x2. By the vector, I mean delta x, that is x2 minus x1. Of course, x2 minus x1 has 4 components. It has the time component and x, y, z components. What we would want, if this vector is pointing to the future, the time component has to be greater than 0, right? So if x2 minus x1, 0 is greater than 0, but this is just warming up. I have a proper definition. We would want this for delta x to be future pointing. And it's not difficult, but I'll just make a big deal about this, again, because everything we do is really in preparation for general relativity, right? So that the language is already there for you. Yes?
Is that just a random superscript 0? What is that 0?
Oh, that's a 0 component. So remember, there are many choices of bad notations that we have. So let me just do it this way. X, if this is a vector delta x, it has various components.
Yeah.
So it would be C, for example, C delta t, delta x, delta y, delta z, right? And when I write delta x0, I really mean C delta t.
Yeah. Well, you see how that would be confusing, correct?
Yeah, sure.
It looks like it would just be always true.
Yeah, and in vectors, and I'll make this distinction right in the next result that we're going to prove. Vectors are not necessarily just difference in points. I've mentioned this before. There could be, the vector potential, you've seen that, the velocity of an object. So this delta x is just a placeholder till we get started. So, this is I'm not defining what future pointing is. This is sort of our hope, our intention. Okay? So I have to make things precise, and given a space-time, and if I tell you there should be a way for me to tell you how time is oriented, and then there should be a recipe for you to tell me if a vector is future pointing or past pointing. Yeah? But this is, so let me clarify, this as a whole. Yeah, it's not a difficult wish, but nonetheless, that's what we want. So to put things in perspective, so let t be a time-like vector. And W be a causal vector. What is a causal vector? It's not difficult, it's just definitions, but we'll use it often enough so that it'll become very natural to you. What are the 3 kinds of vectors we've talked about? Time-like, space-like, and not light-like. What do you think is a causal vector? What can, causality, right? What do you think is, can anything travel beyond the speed of light? Assuming, we know the end story. No. So everything else can affect what we measure, right? So by a causal vector, I mean like or no. Oh, sorry, like or time-like.
Okay.
You know, these are the only things that can affect causality. Again, we'll see all of this. In a typical special relativity course, this is not the language people use. Again, we're not gearing towards special relativity alone. Then either, you have two choices. T0, W0. This is the zeroth component of the vector T and zeroth component of the vector W. This combination is greater than 0, in which case eta T W is less than 0, or
Is zeta still the causal vector?
yes. In which case, eta T W is greater than 0. Again, there's a purpose for this theorem. It is to make sure we can define causality or future pointing in a consistent way. So either T0, W0 is greater than 0, in which case the inner product of the two vectors is negative, or it's less than 0, where the opposite happens. I'll prove one, you can see the other. Just write everything with the negatives. Okay, so T0 squared. I'm going to write this. You guys think and tell me why this is the case. Oh, first of all, note T0 not equal to 0, W0. Why is that the case?
Well, because T0 and W0 cannot be greater than 0 if they're both equal to 0. Or if either of them is
No,
equal to 0.
you know, if can a time-like vector have a zero time component?
Oh, no.
No. Can a light-like vector have a zero time component? No, light has to move in time,
Oh, okay.
right? Space, just a spatial point, it can have a zero time-like component. So this is, okay. Also, tell me why this is true. Just look at one, the other one becomes clear.
Would it not become space-like if it was less than?
That's exactly right. If it's equal to, it would be null. If it's less than, it would be space-like. You just write it out, right? Let me just scribble and erase. Take this and bring it over there. This is a time-like vector, so it has to be less than 0. So I'll bring this over here. So this is light-like or causal. It could be time-like or no. So this inequality also includes the equal case. Okay. Like I said, that's a scribble. So we'll take that off. And so what I have is I'm going to take the 2 and multiply. Greater than the product. Why did I remove this possible equal to? Because one is greater. If I multiply these two, this is greater and greater than or equal to. So it's only going to, the product is going to be greater. Yeah? 3 is greater than 1, 2 is greater than or equal to 2. Then 3 times 2 is going to be greater than 1 times 2, which is 3. Oh, 1 times 2, which is 2. Yeah. Okay. This is a tangent, recall? A dot B, absolute value of A dot B is less than absolute value of, as a vector. We've seen this before because it's actually equal to AB cosine theta, and cosine theta is always less than or equal to 1. This is nothing more than the square root of this is that. Correct? And the square root of this is that. Therefore, I have I can put an absolute value. Not square. A dot B continues to be smaller. So now, I'm going to take the square root and also, so I'm going here. First, let me take the square root. So the absolute value oh, I already put the absolute value. Okay, suppose T0, W0 is greater than 0. So we're doing this part. All I may need to erase this, but all I need to do is show this part. Right? So in this case, this is just T0, W0 because absolute value of a positive number is itself. And what I can do is, well, I can just remove the absolute value because this is positive. I can say this is I equals 1 to 3. What does that mean? What does this mean? Or minus T0 W0, you know the end result. I'm going to write it and you verify it's true. Work it in your head.
It's going to be less than or equal, yeah, less than. Why can't it be less than or equal to 0?
If it's equal to 0, then no.
Oh, sorry, you're absolutely right. I could have removed the equal to a long time ago.
Oh, it wasn't supposed to be there. I see.
Yeah.
I see.
Yeah, good catch.
Gotcha. Yeah.
And isn't that precisely that? And so for the other case, we just flip it. Now you're wondering, yeah, sure, why? This result will enable me to define time orientation. I think this is definition 2.16, but I've edited my notes, which I'll always do a few edits. So we're almost at the end of the chapter. When the chapter is completely over, I'll update the notes and you will have a cleaned up version for now. It's a cleanup is always done. So I don't know how to write this. T be a time-like vector field in Minkowski spacetime. Then the pair M4T is called a time-oriented Minkowski spacetime. Furthermore, what do I want to say? In M4 tau, a causal vector or vector field, either at a point or just everywhere, is future pointing if and only if, can you guess?
That's just T, right? It's not tau.
Oh, sorry, that is tau.
Oh.
A causal vector W is future pointing. This is not tau, this is like a script T. In LaTeX it would be actually I think it's better to write it that way. How many of you started playing with LaTeX?
I've touched it. Just kidding.
It's kind of neat. You can see how you can typeset your notes. Huh?
No.
Have you tried it?
No.
You should. It's kind of fun.
It is, especially when you
Yes,
spend
it's
an hour
pretty
trying
fun.
to figure out
It's
how to make something look
intuitive.
right.
Oh, thank you.
No, there's a little bit of a learning curve.
There is a learning curve.
But when you can see how my equations are all hyperlinked and you can click. I'm not working, I don't have to work at that. It just, the table of contents is automatically generated. So
It does become faster than writing.
once you
Once you actually learn.
I've gotten pretty quick at the word, word equation thing. I gotta write them up real quick.
It's so much easier to use LaTeX.
It is, but I mean, like, there is definitely a learning curve.
in M4T, an inertial coordinate system, or that's all we have considered, inertial coordinate system, is positively time-oriented, and this will make sense now, oriented. If
Is that an if and only if, or just if?
that's a definition. Cool. Is there another row?
Yeah.
In Minkowski, tau, or T, the inertial coordinate system is positively time-oriented if T0 is greater than 0. Now let me tell you why. I'll let you write that down first. First of all, you want a vector to be future-pointing if the time component is greater than 0, meaning you're flowing to the future. But if this is true, suppose you have another causal vector that is future-pointing, which means that is true. Then from the previous theorem, what do you know? W0 times T0 has to be greater than 0. Correct? But T0 is greater than 0. So what must be true of W0?
Must be greater.
Must be greater than 0. So all this abstraction just to catch your nose the long way. End of the day, if you have a nicely oriented coordinate system, a causal vector field or a vector is future pointing if its 0 component is greater than 0, if the time component is greater than 0. Meaning you're not flowing to the past.
What if both vectors were negative?
No. If it's a positively oriented coordinate system by definition.
All right.
Correct. So if you started off with a negatively oriented, we don't talk about it, but you can see it's negative. The other case, it would be negatively oriented. Then all future pointing vectors would have the time component to be less than 0. That's not a big deal. You just pick the watch that goes backwards.
So
It doesn't mean physics is going backwards. Yeah.
we choose T0 to be greater than 0
Yeah.
for this positive time orientation, so that we can then say
Yeah.
that vector W is
Yeah.
future pointing
Yeah.
if eta of TW is less than 0.
But that is always, this is always the case, but if this is the case, for a future pointing vector, W0 has to be greater than 0.
Oh, wait, hold on. Okay, so if,
Well, if W is negative, it would reverse the -1 in Minkowski metric, making it greater than 0.
yeah, but then also if T0 was less than 0.
Well, that's what I was asking. It's just,
Yeah, so if
So that bottom one has to be the case.
well, it's just a
T0
definition of
no,
tau.
but I can pick a time reversed coordinate system
And so now if you have,
where T0 is less than 0. That means all future pointing vectors will have time components to be
negative.
negative.
It's just a math thing more so than any physical.
Correct.
Okay.
Yeah. If you pick a positively oriented coordinate system, your clock is taking the way you're used to.
So now I have a question.
Yeah.
If you say, let's say you have this negatively time-oriented system.
Let's do that. Actually, that's a good point.
Because then if you do that, and then you have a W that is future pointing.
Let's do that.
Yeah.
Let's do that. Suppose,
Space like.
this is not part of your notes necessarily, but let's just do that. Suppose right? I'll also let, I hate to do this, but it's it. What does FPC mean?
Future pointing.
Causal. By definition, is what? No. If you have a vector W that is future pointing, this is by definition always future pointing.
Oh.
Two vectors are future pointing if
But you have T0 less than 0, right?
T0 is less than 0. But if this is the case, we know that T0, W0 has to be greater than 0.
So W has to be negative to be future
So
pointing.
if this is negative, this has to be negative
To be considered future pointing.
to be considered future pointing.
Okay.
So if T0 is negative in one coordinate system, you just decided that in your clock, 4 p.m. comes after 6 p.m. No, after 5 p.m. You want the clock that reads that way. Then every vector will go backwards.
So
Every causal vector will click backwards.
So, okay. Future pointing is not necessarily dictated until after your coordinates are set up.
No, it is, no.
It's
that's not
always true.
It's always, this is what it means. If this is the direction of future, this is what it means for a vector to be future pointing. This relation.
That's why it's causal.
That's why it's causal. That's why it's future pointing causal.
Would W be considered future pointing
Yeah,
in both tau naught is less than 0 and tau naught is greater?
sure.
So it can be both.
Same definition applies. If tau 0 is less than 0 in a coordinate system, then W0 has to be less than 0. If tau 0 is greater than 0 in a coordinate system, then W0 has to be greater than 0.
So one plus the other.
One implies the other. Either for all future pointing vectors, the T0 component is greater than 0 in special relativity, or for all future pointing vectors, the time component is less than 0. Some of you are quiet.
So there can never be a causal vector with the opposite sign of your other vector, like t.
Correct, the orientation vector.
Okay.
Yeah. T dictates the orientation.
Such things as pass pointing.
Yeah, we'll have pass pointing.
Oh, there is a.
Oh, sure.
Okay.
Tachyons.
Huh?
They don't exist.
Well,
Nonetheless,
that we know of.
correct.
Maybe they do exist, like
Yeah.
within.
But is the argument clear?
I think so.
Then look at the previous theorem. That's the C. What I showed you in the previous result, and we're using the previous theorem here. So that's what the theorem showed. So suppose this is less than 0. This is what it means in any coordinate system for W to be future pointing if this guy is. That's what it means. So if this is going to be less than 0, T0, W0 has to be greater than 0. Therefore, if T0 is less than 0, W0 has to be less than 0. And W is any causal vector.
So is there never so there'll never be a causal vector that's past pointing and then an orientation vector that's future pointing, ever?
You can have a past pointing null vector. You can have a past pointing time-like vector, but just past pointing.
But we won't call it W.
No, we can, no. Remember I said this is a causal vector, W is future pointing, if this is true.
Okay. Okay.
So we won't call it future pointing.
So, okay, then I have a question.
Yeah.
Can W be future pointing in one of these vector fields?
No.
And then
No. Future pointing, past pointing doesn't depend on the coordinate system.
depends on the vector.
Depends on the vector.
But if the coordinate system changes,
Yeah,
it's still future pointing?
correct.
So
That's-
if tau somehow goes from being greater than 0 to less than 0, it doesn't change the fact that it's future pointing?
I know what you're thinking. Except I don't want to multiply things by Lorentz transformation.
Oh, great. Oh, you have to transform the vector
Yes.
as once you have this,
Yes.
once tau changes,
Yes,
you have
yes.
to transform the vector so it fits onto this new
Yeah.
vector. Okay. That makes more sense. Okay. Understood.
Let me include that in the homework as an exercise, so that you can tell if you're going to live in the future or your past.
Okay.
Yeah?
Understood.
Work that one through and ask me questions on that. I mean, otherwise I'd be just taking matrices and just multiplying. So I'll add it to the homework list as I update it. Okay. Good. So I used a time-like vector field to define future and past pointing, but I could just as easily pick a like-like vector field. So I'm not going to, this is a problem, but again, all these problems, there are reasons why I'm assigning them. So let me state the problem for you. And I hope the numbers haven't changed, but I think it's problem 217. So I pick a like-like vector field N. It's continuous. It's a null vector field. Okay? And let this be, look at that. FPN. What does that mean?
Future pointing null vector.
future pointing null vector field. Let W be future pointing causal. Then, so you will show the following. I'm writing it as then, but it's a problem. Then eta Wn is less than zero if W is not proportional to N. You're wondering, whoa, what is that? Why did I do? Right? So if I just stopped here, you would be happy. Yeah, you would say, well, life's good. This is what I just saw. Why if it's not proportional to N? Well, come on. If it's proportional to N, what's going to happen? Let me write down the result, and then, let's see. Otherwise, W is equal to some F squared times N. Some function, but it's a positive function. Now, why is that?
So that's,
Because see, then look, this becomes and this is not less than zero, but n is zero because it's a non-vector.
so if W is proportional to N, then that means it's a Lie-like vector.
Correct. It's a like vector with a positive coefficient. Therefore, if this is future pointing, W is also future pointing.
Has to.
Because F squared is positive. That's why I picked F squared instead of just F. It's a positive function. Yeah? These are all great problems to spend lots of time on. Like hours and hours. Sometimes if you think the right way, it's a two-line problem. It is a two-line problem. But we're learning this, so. But these are just great things to work on. I mean, you're working on past and future. It's not like, calculate the spring constant of the spring.
Sometimes I miss it.
Yeah, these are all problems, but they're lightweight theorems is what they are. So you're working at that very abstract level. Oh yeah, so this is a nice, I'm not even going to number this anymore, but I'm covering topics exactly the same sequence as the notes, but as I move things, the number change. So let W, B, F, E, C. In a positively time-oriented coordinate system, X, Y, Z in comma, and I'm going to pick something that we have forgotten. I'm going to pick an element of the orthogonous Lorentz group. Because we have somehow, using the word orthogonous, we have assumed that these guys preserve the direction of future. Like, maintains chronology. We'll just show that. Then, W bar is also FPC, where W bar in CT bar, X bar, Y bar, Z bar. If you recall, you know how these two are related? Exactly by this lambda matrix. Yeah? Okay, so in particular, this guy is also positively oriented. Proof is very simple.
So is this just like an embedded Lorentz transformation?
Yeah, this is a Lorentz transformation, but not any old Lorentz transformation. It is the orthogonal Lorentz transformation. Again, this is just definition. What does orthogonal mean?
That the first index is positive.
0, 0 is greater than 0. In fact, they have to be greater than 1.
Yeah.
Greater than or equal.
Yeah.
So, and this is good. This is just good to periodically visit. What are Lorentz transformations made of?
A rotation matrix.
Very good. 2 rotation matrices and 1 boost. Rotation matrices, do they mess with the time component at all?
No.
No. The only thing in between is the boost matrix. And the boost matrix, we can always choose it so that it's in the x direction. So I'm just going to not worry about the rotation matrix. And I'm going to pretend that this guy is a boost in the x-axis. And then I'm going to look at the 0 component. And just like any time component of a vector, this is what that is my 0th component of the transformed W. Yeah? See, the CT equals gamma CT minus beta X. That's what this is coming from. Okay? But what do you know? That means I can bring this to this side. And if I sum the square, it's less than W0. I'm not summing the square here, I only need 1 component. Yeah? If this is true, is this, watch it. If this is true, is this true? If I add 3 positive numbers, if it's less than this, if I pick one of the 3, and then has to be true. Is this guy already positive? So first of all, I have taking the square root. But this is future pointing. So is this positive? In the old coordinate system?
That is not positive.
This can be positive or negative. It can have an x component or minus x component. We don't care. But even if you take the absolute value, it's going to be less than that. Is beta less than 1? Beta is V over C.
So it has to be less than 1.
Less than 1. So is this greater than 0?
No.
Even if it's 1, it is greater than 0.
Or sorry, it will be greater than 0. Always.
Yeah. So that means this is greater than. So what does orthogonal Lorentz transformation do? Take future pointing vectors to future pointing vectors. Can you guess what non-orthogonal Lorentz transformations do? Flip it. And that is why, of the entire bag of Lorentz transformation, we decided to live with, we said we're going to look at the Lorentz group. And the Lorentz group is a subgroup of the general Lorentz homogeneous transformation. What subgroup is it? It's the orthogonal subgroup. Why do we restrict it to orthogonal subgroup? It preserves the direction of future. All of a sudden, an introductory course in special relativity just gets a little tighter, right? Not with difficult math. This is just algebra. If the math, if calculus gets difficult, it's not difficult at all. When words get to be difficult, you have to let this sink in. Read it a million times. There are a couple of things I want to, the fun part, and we can even discuss after that. But here's a nice little problem. If you take two future pointing vectors and you add them up, what are you going to get?
Another future pointing vector?
Another future pointing vector. But before I do this, here's a problem. This is find a vector. Find a space-like vector. This part is easy. Space-like vector S such that S0 is greater than 0. When I say this, I mean do something like 0, 1, 2, 3. Like find a vector in a Minkowski space. Because we're going to provide a counterexample. We don't need theorems. If you want to disprove something, we just need to give one counterexample. So what is it we're trying to do? And then find a Lorentz boost. Lorentz boost such that yep. Now this has got to be very interesting. You cannot do this with time-like vectors. Time-like vectors preserve future. Can you do this with null vector? No. Space-like vector in one coordinate system can have S0 greater than 0. Then you use a Lorentz transformation, an orthogonal Lorentz transformation, and you can find a space-like vector whose now transformed zeroth component is less than 0. What is the moral of that story?
Wouldn't that make it a time-like vector?
No. Only S0 component. There's a moral to this problem. This is a course on morality.
That space-like vectors break physics?
There is no temporal order to space-like vectors. You cannot say a space-like vector is future pointing or past pointing. Just great how things just consistently follow through, right? Yeah. So I think I've dragged you through the mud today. It's not difficult stuff. It's just algebra. But there's so much meat. And this next time when we meet, I'll just state the Zeeman's theorem. I won't prove it. Not because it's difficult. It's just long. It's algebra. It's just long. But I'll clarify the meaning and its purpose. But today we have covered a good bit about time orientation. This will serve as a guide in any course in relativistic physics, be it general relativity, string theory, it doesn't matter. Quantum field theory, these precise notion is sufficiently abstract. Okay, so we have 2 minutes. I'm just going to turn the camera off. I'll take more questions.